Hi, we're now on to our second presentation in this series, which is Hyphenating GCMS, and now we're going to look at it from the MS perspective. So first of all, mass selector detectors, or mass spectrometers, can be universal. That means we're running them in scan mode, and we're looking across a certain mass range. Or they could be selective. For example, we're using SIM mode, which is a selected ion monitoring mode, where we're only looking at a few selected masses that we're interested in, and these are representative of the compound that we're interested in our analysis. So when we think about mass spectrometry itself, it's a technique when hyphenated to GC is used to identify unknown compounds in our sample, quantify known compounds, and also to determine structural and chemical properties of the molecules. Compared to a GC detector, when we're hyphenating GC with a mass spec, we produce three-dimensional data. Therefore, the mass spectrometer is adding an extra dimension. So this is the mass spectrum itself, and this is the information which enables us to identify the compound. So the first part in GCMS is the gas chromatograph, where we get chromatographic resolution. So we're separating all our peaks from the matrix and from each other on our analytical column. But having a mass spectrometer at the end also means we can use analytical resolution. And this is the difference between the masses that can be used for separating analytes. This means that we don't have to always have total chromatographic resolution to be able to identify or quantify compounds which are coming out at a similar retention time. However, peaks that have 100% coelution cannot be deconvoluted or identified. So therefore, we will need some chromatographic resolution if we to get a very much higher quality of data, particularly for identifying unknown compounds. If we look at the peak here, you can see the total ion chromatogram, which is the black line just here, and that is what we'd see in our normal chromatogram. But if we go and extract three other ions, here the 105, the 94, and the 176, we can see that we actually have three different compounds underneath the TIC. The TIC itself is a total ion chromatogram. It's the sum of the abundances of all the individual masses that we have acquired in our mass spec method. So if we were to look at these, and we knew that these three compounds were there, we could easily extract a unique mass for each of those to then go and quantify, but also as well to determine where to look at for obtaining a mass spectrum. But if these were unknowns, we might not even know that we have coeluting peaks. So therefore, techniques like deconvolution will be very, very useful to identify that we have coeluting peaks, but also to pull apart the mass spectra used for library searching or structural analysis. Now let's have a look at the mass spectrometer itself and the different components. So if we have the GC on this side, we have a transfer line. This will then transfer the column from the GC into the mass spectrometer. The mass spectrometer itself is under a vacuum, as we discussed in a reasonable amount of detail in the last presentation. The key components of a mass spectrometer are the ion source. This is where we take our neutral molecules and ionize them. The ion optics, which then focuses the beam of ions through the rest of the mass spectrometer and into the mass analyzer. This is where we now separate the ions based on their mass-to-charge ratio. Once we've separated them, we then need a detector to count the number of ions of each mass. This information is then taken out to the data system, which will produce our chromatogram and also our mass spectra. So think about the vacuum system with a GCMS. First of all, it's two components. The first component is a high vacuum pump, and then that feeds into the four-line pump. Now, the four-line is also known as the mechanical or rough pump. This is used to reduce the vacuum to 10 to the minus 1 to 10 to the minus 2 torr. It has a very high capacity because it's taking all the air molecules from the room and starting the pump down process. but it can't take it down lower than about 10 to the minus 2 torr, which is not low enough. It's not a good enough vacuum for a mass spectrometer. Therefore, we then have a high vacuum pump. This takes it doesn't have a high capacity, but is able to take our vacuum down to about 10 to the minus 5 to 10 to the minus 2 torr. Now, this vacuum system itself limits the amount of flow that we can get out of our GC into our mass spectrometer. If our high vacuum pump is a diffusion pump, it will only cope with flow rates from the GC of up to about 2 mils a minute, although I wouldn't be going above 1.5 mils a minute to get a good sensitivity. If the high vacuum pump is a turbo pump, this could cope between 3 and 15 mils a minute, depending on how large the turbo pump is, or it could be a mass spectrometer with multiple turbo pumps. So as you can see, that's quite a wide range. So knowing what system you have, knowing how higher flow rates you can use is very important when setting up your GC method, just to make sure we maintain a good vacuum and therefore good sensitivity. Now the GCMS interface is the transfer line between the GC and the mass spectrometer. The GC isn't under vacuum, it's at ambient, which is 760 torr, and of course when we're optimizing our flow rates on our analytical column, it could be between 0.5 mils a minute or 15 mils a minute if we were using something like packed columns. The mass spectrometer, of course, though, needs a vacuum in which to operate, and this could be between 10 to the minus 5 to 10 to the minus 7 torr. The flow rates it can cope with to maintain a good vacuum could be less than 2 mils a minute if we had a diffusion pump, or between 2 and 15 mils a minute. Therefore, on the GC side, we need to be using columns which can operate at the flow rate and give us good separation, good resolution at flow rates below what our vacuum system can cope with. So generally on the GC, you'll be using narrow ID columns of less than or equal to 0.25 millimeter ID. So it's lower flow rates means we get an improved MS vacuum and improved MS sensitivity. Also, we don't want to be installing more than one column into the mass spec unless we're using a high-performance turbo which can cope with high flow rates. On the mass spectrometer side, we need to know the pumping capacity of our instruments. As I said, diffusion pumps very low flows, turbos depending on how big they are, much higher flows. And if we're using chemical ionization, we should be using a mass spectrometer with a high-performance turbo because the additional gas for the CI will increase the flow rates into the mass spectrometer and, of course, reduce our vacuum. So when we're optimizing a mass spectrometer, first of all, we should always think about leak checking before tuning, unless the software, of course, checks automatically for leaks. We don't want to be choosing a mass spectrometer if we have a leak into it. And, of course, because of our GC, we've got several different places where leaks can occur, and these leaks could actually just occur overnight. When we're about to perform our tuning of a mass spectrometer, we should be setting up the flow rate and the different temperatures within the GC and the mass spectrometer, all exactly the same as what we'd be using actually within our analysis method. This means that we're tuning at the method temperatures, the method flows, to get the best sensitivity and stability of that mass spectrometer. We should also consider the detector when optimizing the GC chromatography, say, for example, peak width. As talked about in the last presentation, we don't want to be getting lovely, very, very narrow peaks out of the GC, which will give us good signal to noise, but if our mass spectrometer cannot acquire the data fast enough, we'll then either get too few data points across the peak, which means that our quantitation or our qualitative analysis would then be reduced because we don't have such a good quality of data. So we should be optimizing a mass spectrometer, the number of cycles per second for the analyte peak width. So have a look, what's your average peak width from your chromatogram? Is it 3 seconds, 6 seconds, or 1 second? Different instruments may also have different tools to improve the sensitivity further. For example, we might be able to optimize the threshold value. We could go and do some signal smoothing, etc. Now, of course, with GC detectors, they can cope with large solvent peaks, but mass spectrometers are very, very sensitive. And solvent peaks contain very large numbers of molecules. If we try to ionize all of these molecules from the solvent, then we'd reduce the lifetime of the filament, or it would be immediately broken. So therefore, when we're using a mass spectrometer, we need to be thinking about using a solvent delay. This turns the filament, the MS acquisition, and data recording off while the solvent exits the column, and then it turns it back on as soon as the solvent's gone to then start saving and acquiring the data from our first peak. So when we're optimizing time taken for the solvent to elute, we can either start to do it experimentally. So we start with a longer delay and then reduce it until we can see the solvent tail. If we're transferring the method from a GC with a different detector across to our GCMS, we could have a look at the peak width and see approximately how long it takes. But also, if we have a mass spectrometer where we can see the vacuum gauge, when the solvent goes through the mass spectrometer, the vacuum gets worse. And then as the solvent starts to reduce down again, down through the solvent tail, it will then start to improve the vacuum again. This will then show us the end of the solvent delay time. So if we have a look at the chromatogram here, this is where our peak would be, our solvent peak would elute. And of course, we need to make sure that we turn the mass spectrometer back on again immediately before the first compound of interest elutes, otherwise we will not see it. So when we're optimizing the mass range or SIM ions, we should be thinking about if we're optimizing our mass spectrometer in scan mode, we need to be reducing the scan range down so it's just wide enough to detect all the masses needed for our method. So what's the minimum and the maximum ions that we'd like to see. If it's as narrow as possible, this means that we have less steps. So if it's a scanning instrument, we'll be having a step for every single ion that we're acquiring in our mass range. If there's less steps, that means that we'll have a faster faster scan rate. When we're thinking about the low mass in our mass spectrum, if we go too low, we'll see air, but if we also go too high, we would miss key fragment ions, which could be used in identification of that compound. When we're thinking about the high mass in our mass range, if it's too low, we could miss the molecular ion, again, very important for identification of that compound. But also, if it's way too high, it will take lots of time scanning up to that mass, that high mass, and therefore increase the scan time. Therefore, we won't be getting as many data points across our peak. So we need to be thinking about where the high mass will sit. When we're optimizing our scan range, we should try to avoid, if possible, the 44 ion. This is representative of carbon dioxide, which will be in the background. So think about starting at 45. If we need to go lower, think about argon at 40, so we could start at 41. If we need to start lower still because we're looking at very volatile compounds, we could try and avoid the oxygen peak at 32, so we could start at 33. Lower again, we want to certainly avoid the nitrogen peak at 28, so we could be starting at 29. Particularly important if we want to analyze something like methanol, which a key ion there is 31. And even if we want to go lower still, trying to avoid the water peak at 18, we could start at 19. We also want to try and avoid the column bleed and matrix ions for SIM methods, so where we're choosing individual ions. We don't want to be choosing ions which are in our background. Remember, though, that scanning instruments, the larger the mass range, the more steps there will be, the longer it will take to scan, and therefore you'll get less data points or less time, i.e. the step length, on each mass. This means that we will have less sensitivity or less data points across our peak. If we're using a mass spectrometer, which is a simultaneous acquisition instrument, the larger the mass range, the much larger the data files will be. So I've been talking about data points. Let's have a look at data points and think about how to optimize this. So if we look at this peak here, we have got 7 data points across the peak, which really is not large enough to fully outline the edge of that peak itself. If we were to quantify this if we were to quantify this peak, then the area could slightly change, even if the amount of the analyte going through the GCMS system is exactly the same. So if we have too few data points, integration of the peak area is not reproducible, and we might not be able to see any peak coelutions if we want to use analytical separation. If we get too many data points across the peak, we get quite a noisy peak, and that reduces our sensitivity. So how many data points across the peak depends on what you want to do. So typically it would be between 10 and 15 for qualitative analysis and 15 and 25 for quantitation, where we want to measure the peak area. And the scan rate that we need depends on the peak width and also the acquisition rate of the mass spectrometer. So if we have the mass spectrometer acquiring a rate of 5 cycles per second, and our chromatographic peak coming out of the GC is only 0.5 seconds wide, that means that we'd only have 2.5 data points across that peak. That's certainly not enough to even see that there is a peak there. If the peak was 5 seconds wide and we're running it at 5 cycles per second, that will give us 25 data points across the peak, which is plenty for both quantitative and qualitative analysis. So we need to go back to our GC and look at our average peak width. So this is how it affects our peak shape. So as the acquisition rate or the scans per second reduces, we get less data points across a peak, meaning that we get worse peak shape. So if you look down here, this is only 1 hertz, so the peak shape is horrendous, and also it's very, very broad, so coeluting peaks would occur. The peak apex is also more difficult to point. Would we take it as the average point here, or would we take it there? So therefore, if we're identifying peak based on retention time, that retention time would be shifting around depending on where those data points exactly are. Signal to noise also reduces. You can see this peak is much smaller here than it is if we look at 60 hertz. The peak area varies. Even if the same amount reaches the detector, quantitation is not accurate. And coelutions could also be more difficult to spot and also get a good mass spectrum for library searching. Another effect is spectral tilting or spectral skewing. Now this is only only occurs with scanning instruments. So if we're scanning from high to low mass, so if we look at this point here, when we're scanning down at the up at the high mass, we have not many ions going through to the mass spectrometer. By the time we've then scanned all the way down to the low mass, we'll be getting quite a lot of ions coming through. Therefore, we get a skewed mass spectrum like this. When we look at the high mass, there are not many molecules getting through to the mass spectrometer. At the low mass, there are lots. If we're scanning across here from A to B, again, we can see there's an even bigger there's quite a big change in concentration. On the opposite side, of course, what we'll be doing is scanning at high mass when there's lots of molecules getting through to the mass spectrometer, but as we get down to lower mass, there'll be a lower concentration of molecules. And therefore, our mass spectrum is skewed in the opposite direction. So if we don't have many data points across our peak, we will see that the mass spectrum will vary depending on where we take that mass spectrum across the peak. So it's most apparent when we have fewer data points across our peak. So how can we improve this spectral skewing or spectral tilting? First of all, the more points we have, the smaller concentration range there will be. Also, we might want to average the mass spectrum across the peak. That means that the skewing on one side of the peak is then counteracted by the skewing on the other. And if we were taking a single mass spectrum of the peak itself, we would want to be taking it at the apex, because there we'll be getting the least amount of change in concentration. So when we're optimizing our acquisition rate, this affects the number of data points across the peak. So we optimize it for the method average peak width. So what's the average peak width of our analytes coming out of the GC? So for qualitative data analysis, it could be between 10 and 20 data points across that peak. But for quantitation, we want a higher number of data points, usually around 15 to 25. Different manufacturers and different instruments use different ways to adjust the acquisition rate. So scanning instruments are usually based on cycles per second, so that's one full scan, and that usually depends on the mass range, plus the sampling time or the event time. And this depends on how long it allows the ions to reach the detector of a certain particular mass-to-charge ratio. Or if we're using something like an ion trap, how long does it take to fill that trap? When we're dealing with simultaneous acquisition instruments, like a time-of-flight mass spectrometer, we then set the acquisition rate. We don't have any problems with spectral skewing, but the higher the acquisition rate, the lower the sensitivity. Also, mass resolution could also be affected with simultaneous acquisition instruments. So the optimal acquisition rate can only be finally optimized once the GC method is finished. So therefore we can see exactly what is the average peak width. If the GC separation is adjusted, we need to check the number of data points. So for example, we make our GC method twice as fast. That means we're going to need to scan or have an acquisition rate twice as fast. So the first thing we do is enter the scan range. So that will determine how many steps there are. We then check the average peak width in seconds at the baseline, down here of our peak, coming out of our GC, and we divide the required number of data points, depending on if we want qualitative or quantitative analysis, by the peak width to give the required spectrum per second. So, for example, if we wanted 15 data points across our peak, we then divide 15 by our average peak width, which in this example is 3 seconds, and this means we need to optimize it to get around 5 scans per second to get about 15 data points across our peak, which is good for both qualitative and quantitative analysis. We would then adjust our sampling rate or the interval to obtain that optimal rate. So, moving on to our system transfer line temperature. So, some manufacturers recommend that it's 40 degrees below the final oven temperature. But what we've got to remember is, at the end of the transfer line, there is a vacuum. So that means that quite often the analytes reaching the transfer line will move through much faster because we have a vacuum sucking through at the other end. Other things we need to think about with our transfer line is the column maximum isothermal temperature. Because the transfer line itself is at a constant temperature, damaged columns will bleed directly into the mass spec, meaning we need to clean them up more often and we'll get a lower sensitivity. And also we can get damaged columns will also cause activity within the transfer line as well. So we need to make sure that the transfer line temperature is at or below the maximum isothermal temperature of the column. We could use the activated fused silica through the transfer line instead of our analytical column, of course, then it won't be a problem. Standard temperature in most methods is about 280 degrees for our transfer line. Some instruments we can also decide in our mass spectrometer method about high or low mass resolution. So if we work at a high mass resolution, then of course it means that we can see individual masses very, very easily, whereas with a lower mass resolution, we will not be able to see peaks. We won't be able to separate masses quite so well, but that's not a problem if we're doing something like selected ion monitoring mode where the masses are quite far apart. And by reducing down our mass resolution, it means that we get a bigger peak and therefore we can get better sensitivity. So, for example, with a quadrupole, increasing the peak width gives us more sensitivity, lower mass resolution, but reducing the peak width here will give us a higher mass resolution but lower sensitivity. So we need to set it up to optimize it for our method. MS temperatures then, ion source temperatures, most of them these days will reach between 300 and 350 degrees C. Most methods are setting around about 230 degrees C. So we want to be using a moderate temperature which is high enough to prevent condensation of our analytes within the ion source, keeps them in the gas phase, but also minimal to reduce analyte degradation or reactions, especially if you're using something like hydrogen as a carrier gas, which is a reactive gas. EI temperatures tend to be around 200 to 250 degrees. If we're using positive chemical ionization, we tend to be using higher temperatures, around 300 degrees C. And if you're using negative chemical ionization, they tend to be low, around about 150 degrees C, which reduces fragmentation and enables us to get a better molecular ion. Some applications, though, has been work done which recommends higher ion source temperatures. For example, the analysis of polyaromatic hydrocarbons in GCMS. By using higher temperatures, it reduces the absorption effects in the transfer line and the ion source of less volatile PAHs. So therefore, having a transfer line temperature of at least 280 degrees C and an ion temperature of around 300 degrees will actually help to improve our sensitivity. If the analyzer, the mass analyzer, for example the quadrupole, is heated, this tends to be at a lower temperature than the ion source. Another parameter that could be in your mass spec method is optimizing threshold values. Now, if our threshold value is set too high, we will miss seeing all of the small ions within our mass spectrum. Of course, things like the molecular ion is very important for identification of that compound. So what we want to do is just set the threshold value just above the baseline noise, but so we can still see the ions of interest, which will help to identify that compound. If you see extract a certain ion and you see a flat baseline, this usually indicates that your threshold value is set too high. And one of the last parameters in our method that we want to optimize is our detector voltage. This increases the size of the peaks, but also increases the size of the noise. It doesn't always improve your signal-to-noise values. Depending on the instrument, it could be a maximum of 2,000 or 3,000 volts, but the higher the voltage, the faster you'll use up the electrons within the detector. Some specify that if you add 50 volts to your method, you'll be doubling your signal-to-noise value, but that's application dependent. So if you use higher voltages, it reduces the lifetime of the detector, and it can improve sensitivity. But the first thing you need to do to improve sensitivity is get more ions into the mass spectrometer. The more ions you get through the GC system, the better you're going to be, better sensitivity you'll have. So, for example, if you're thinking about a camera, if you have optical zoom, you're actually physically zooming in to see a view much better. Digital zoom is just enhancing what you can already see. And finally, how to deal with mass spec data, particularly from the GC perspective. So the GC column will be bleeding all the time, which produces a background of column bleed ions within our mass spectra. So when we're taking a particular mass spectrum at a certain scan point, this will include the GC column bleed and the matrix ions. It can also include coalescing peaks and also may suffer from spectral tilting, as discussed earlier. So therefore, to obtain a very accurate, cleaned-up mass spectrum for library search and identification, first of all, we go and average the mass spectra across our peak to eliminate those spectral tilting effects. And we could also take an average of our background and subtract it from one side of the peak, and also subtract the other side to remove those ions from column bleed, but also as well if we have some coalescing peaks as well. So that's looking at a GCMS method, more from the mass spec perspective. Any questions?